us continue our discussion of moment of inertia. So far we have taken several examples, but all those examples were in 2D. Today let us take some examples in 3D, that is we are going to talk about moment of inertia of extended objects in 3 dimension. Now the difference between 2 dimension and 3 dimension is the following. In 3 dimension there are, in the most general case, we have to deal with 3 independent axes of rotation. In 2 dimension, if the mass distributed in only a plane such as my hand and then this is rotating in the plane, then it is only possible axis is perpendicular to the plane. However, in 3 dimension this there is not a single possible orientation, but there are any possible orientation, and in general, as you know, that any direction can be represented by 3 independent orientation in 3D. So, we are dealing with 3 independent axes of rotation, which means that there will be at least 3 components of moment of inertia. So, this is why 3 dimension is little bit more complicated than 2 dimension. So, we take some simple example of particularly symmetric mass distribution. So, let us first take a spherical shell of mass m and radius r, and we take an axis of rotation as any diameter, that is any axis that is passing to the center of the shell. In this case, the standard, so one can calculate by applying the definition that we have discussed so far, one can easily calculate the moment of inertia. This calculation is particularly easy if we use spherical polar coordinate system, which we have not discussed in this course. So, I am going to skip the calculation part and give you the result, and any standard textbook will contain the derivation of this result. Probably you have already seen that derivation in high school level. And then we can also take another example, which is the right side, is that instead of a spherical empty shell, we can also take a solid sphere. It is a solid sphere of mass m and radius r. So, now the shape of the object is same, but it is the sphere is filled, not empty. So, we see that the answer, the moment of inertia, will be different. In fact, the moment of inertia is now smaller compared to the spherical shell. This reminds us of the analogous result in 2 dimension, where we saw that a filled disk has same mass and same radius have lower moment of inertia compared to a ring. Now, if you take go to any textbook, you will find lot of standard examples of different simple shape, such as a rod. So, now this rod is no longer one dimensional, we consider that as kind of a pipe. So, it has some but small but finite diameter, and so you have to specify now. So, let us say we are this G represents the center of mass of the rod, which is the middle point, and then we consider a reference frame cut x and y and z as shown in this figure, which is passing through the center of mass. Now, in this particular frame, the moment of inertia about the y axis and about the z axis are 1 by 12 ml square. Similarly, we can take a thin rectangular plate, and again we are considering a reference frame where the origin is the center of mass of the frame, and then the xyz direction as shown, and then we have some standard result. We can also take a rectangular prism, a thin disc in circular cylinder, circular cone. So, some of these simple shapes that I have listed here. So, in all those cases, remember that the origin is at the center of . So, there is some relation between calculation of moment of inertia and calculation of center of mass. Often we need to know calculate the center of mass position first to calculate the moment of inertia. Now, these examples, there is one thing I want to say now. So, you see that here you can take an approach that okay, these values results are listed in the textbook. So, so these are kind of available ready made. So, why should I bother to calculate moment of inertia myself? So, the point is that here these results are given to you ready made, but they are of limited use. Why? Because these results are valid, all these results are valid only for some special shape of the object first. Second, for a special choice of the reference frame, which is but about in which kind of, so this axis of rotation in each of the case, if you think about it, we are choosing the axis of symmetry of the object as our axis of rotation. Now, in practical situations, in real life situation, I will show you some examples. These two things are often not possible. That is, if you are dealing with some objects which are not some simple shape as this, but more complicated shape or even irregular shape, then it is not easy always to immediately guess where is the center of mass by symmetry. The symmetry argument fails. Similarly, if by looking at the object, it may not be possible to guess what is the symmetric axis of symmetry. So, if the symmetry argument fails, then we have no way at this moment to calculate the moment of inertia. But suppose we want to calculate the moment of inertia, you want to calculate the moment of inertia for further analysis of the project or mechanical problem that you are having. For example, you may be doing a project on robotics, and there you are not dealing with some simple objects such as this. So, what we need is a method which of calculating moment of inertia which you can use in arbitrary situation. So, this is something that is a powerful way of it's kind of a mindset. So, it's a powerful way of thinking. So, whenever you are dealing with a problem, so not you should not be satisfied just by knowing the solution, but you must be interested to know the method by which you can yourself find the solution. So, here is the definition of how can you generalize the moment of inertia about arbitrary axis in for a three-dimensional object. So, I am taking 3 dimension because that is the most general case. You can also, but these things are also applicable in 2 dimension, 1 dimension, etc. So, what we have here is that I have written this, as I said, that in 3 dimension there are in general 3 possible axes of rotation, but here I am not making any guess or any constraint that they should be axis of symmetry. They can be not an axis of symmetry, arbitrary choice of axis, x axis, y axis, z axis. So, you take any point in 3D as your origin, not the center of mass, but any point, then you draw some x axis, some y axis and some z axis. Then the moment of inertia, the 3 components are defined as the following. So, the first component Ixx is given by this is the definition. So, you consider a particular mass element dm in space which is located at some point with Cartesian coordinates x, y, z. Then Rx square. So, you are going to calculate the moment of inertia about x axis. So, that is you calculate the distance of this mass element from the x axis. So, this represents the distance of dm from x axis, and from Cartesian coordinate geometry this is y square plus z square. Then you sum over all the mass elements available in the mass distribution. So, that is the integral. So, note that this is a 3-dimensional integral, it is a volume integral. So, it will be clear very soon. So, and similarly you can calculate the moment of inertia about y axis, and this is moment of inertia about z axis, analogous formula. So, this gives you a physical meaning. Now we understand what is this moment of inertia about x, y axis, y axis, z axis mean. It means that, so we want to know the spread of a mass. So we have a mass distribution, some arbitrary object, and we draw our reference frame, the x axis in our reference frame, and we want to know that what is the spread of that mass distribution from with respect to the x axis, which means we are looking at not only the mass but also the distance from the x axis. So, the combination of these two will give us the moment of inertia. So, this moment, this x I axis, this measures the spread of the mass distribution about your axis of rotation. Now, note one important point, I have used two indices. The reason will be clear in coming few lectures. So, I just wanted to highlight that often in some textbooks you will find that the moment of inertia is about x axis, y axis, z axis are represented by a one single note index like Ix, Iy, Iz. I prefer to use two indices to sort of, so that when we discuss the our next concept, the product of inertia, which requires two indices, hence I put two indices here. The other point is that, so often in some another variation in the textbook you often find is that, suppose the object has a finite density, constant density, uniform density. So, rho is the density, that is, if the mass of the object is m and its volume is v, then m by v is rho and this is constant. Then this dm, remember dm is rho times dv, and then you can take this rho outside the integral, and hence it will become a pure geometrical. So, the whatever integral presents is a pure geometrical property of the object and it is just a volume integral. So, now we see that this is, even though I have shown only one integration sign, but it is actually a volume integral. So, we are doing three integrations. So, let us now take an example, and in this example, even though this is a example with a planar object, a lot of aspects about moment of inertia calculation and various tricks will be evident I am going to use in this example. So, you can so pay attention to this example. So, here is kind of a practically important example, because here we want to calculate the moment of inertia not of a simple shape, but a combination of simple shape. So, the composite object. So, remember it is analogous to what we did earlier to calculate center of mass. So, it is something similar. Here also we are going to calculate, instead of center of mass location, we are going to calculate the moment of inertia of the shaded, the blue shaded region. So, the blue shaded region you cannot describe as some simple shape, but you can think of it as the rectangular plate, which is a simple shape for which moment is easy to calculate moment of inertia, and the hemisphere. So, then you can sort of see, so the idea is that we calculate the moment of inertia of this plate, and then we calculate the moment of inertia of this hemisphere or semicircle, and moment of inertia of this rectangular plate. Then we get the moment of inertia of, if you subtract, then we get the moment of inertia that we desire. So, here let us compare with moment of inertia and mass. So, there is a pretty crucial difference. Difference is the following: in the case of a mass, we can always take a mass, and if we scoop out this portion, then the mass of this rectangle minus the mass of this semicircle is going to give us the mass of the composite object as shown in the figure. However, moment of inertia not only depends on the mass of an element, but also the distance from an axis, which means that this subtraction you can only do if you are calculating all moment of inertia in the same reference frame about same origin and axis of rotation. So, this is something you should keep in mind. Only then we can do this simple subtraction. Okay, so let us proceed. So, first let us do the calculate the moment of inertia of the rectangular plate. So, this is our origin and let us say this is B and this is H. So, the dimensions are given. So, what is the moment of inertia of this particular object? So, in this case we are going to do the following. So, take a mass dm at a point x y. So, we want to calculate the moment of inertia about the x axis. So, the distance of this dm from x axis is y square dm. So, this is our target quantity. So, this is y square, dm is dx dy. So, this is, let us say the area density, that is mass per unit area is sigma, then and the area element. So, if it is a rectangular element of with dx and height dy, then the area is sigma dx dy. Sigma is, I assume sigma is constant. So, I will take it outside the integral. So, this is going to, this will become sigma times dx times y square. Okay. So, yeah. Now, so note that this is a rectangle. So, x and y coordinates are independent of each other. So, I can sort of pretend that these are basically product of two one dimensional integral. And now I need to put the limit, and the limits are from, for x goes from 0 to b and y goes from 0 to h. So, we have for the rectangle. Now, let us come to the calculating the moment of inertia of the semicircle. So, let us draw it. So, the semicircle is something like this. So, from this point is at the point b by 2 and this is h. Now, for the semicircle, we in our list we did not probably calculate the moment of inertia of the semicircle. So, note that we want, the problem asks us to calculate the moment of, so this system of axis that is given in the problem is not an axis of symmetry for the semicircle, because it is not even passing through the, first of all it does not pass through the center of mass, and of course the mass distribution of the semicircle is entirely on one side of the axis. So, it is not symmetric about x axis given in the figure. So, how to calculate the moment of inertia of the semicircle? So, here we can use some our tricks and our parallel axis theorem. So, the first thing is that it is easy to calculate, let us say if we, instead of semicircle, so this is our first step, instead of semicircle, if we have a full circle, a solid disc filled circle, in that case we know and we consider an axis which is parallel to the x axis, let us call that a prime. Now, about this axis and this semicircle, this filled circle, so this is the filled circle, this is the filled semicircle, this we know, or in our result it is given. So, the moment of inertia, so let us call that this point as C. So, I x x about C, where let us call that, let us say x and x prime. So, x prime about c, this we have seen before, this is 1/4 the mass times the radius of the circle r square. Now, if we about the same axis, so this is about x prime passing through C, which is the center of the circle. So, if we have a full circle, center of the circle is the center of mass by symmetry. Okay. So, then if I take now cut the upper half, then for the rest of the half about the same axis, we can simply say that this is just of the for the semicircle. So, this is for the full circle, let us call it I prime, and this is I x prime c about the semicircle about the same center and same origin and same axis will be half of 1/4 m r square, by symmetry is just half of the full. So, this is 1/8 m r square. But now C is not the center of mass of the semicircle. So, it is clear that the center of mass is no longer at this point, but it will be somewhat down, somewhat to the middle, because this is a point about which the semicircular mass distribution is more or less kind of balanced about it. It is kind of a center of the semicircular mass distribution. So, it is somewhat lower. So, let us call this point as Cm of the semicircle. Now, this we have calculated the center of mass of a quarter of a circle in one of the earlier lectures. So, I am not going to show, you can generalize that that result. I am going to use that result, but it is easy to show that the center of mass will be located of course, it is by symmetry, it is clear that this will be along this line that is passing to the center of the semicircle and parallel to the y axis, and it will be located at a depth d, where d is given by 4 r by 3 pi. So, this is some analogous to the result we derived calculated in some other earlier problem. So, then the center of mass, its coordinate, that is its distance from the x axis from x axis is h minus t. Okay. So, now if we can apply parallel axis theorem, and if it says that if the center of mass, if we take an axis, so let us draw the picture again in a zoomed in way. So, we have taken this axis and calculated this the moment of inertia. Let us take another axis, and remember that this is our original x axis about which we are supposed to calculate the moment of inertia. Now, we take another axis which is parallel to x axis and passing to the center of mass. So, parallel axis theorem says that means the moment of inertia about the axis x1 prime, which is passing to the center of mass, is given by the Ixxc minus m d square, which is 1/8 m r square minus m d square. but we are not finished because we have to, our target axis is the x axis. So, again we can apply parallel axis theorem and calculate the moment of inertia about our target axis now, which is and this distance. Now we need to look at this distance, and this distance is h minus d whole square. So, if I plug in everything, we are going to have and then we are going to have so now this is our required moment of inertia of the semicircle. Well, we derived some expression. So, now we need to put the numerical values. So, this I leave to you as an exercise to complete this calculation and plug in the numerical values. So, I will provide some hint. So, according to the problem, some of the stuff are given. So, R is given as 90 millimeter, the H is 120 millimeter. Now, the mass you can calculate to be, so D we have just mentioned this, and you can show that this turns out to be about 38.2 millimeter. Then our H will be H minus D will be 120 minus 38.2, which will be about 81.8 millimeter. Now, we need the M. M is the mass of the hemisphere. So, mass of the hemisphere is, if the density is sigma times pi r square by 2. So, let us assume that sigma is 1 gram per millimeter square. So, take this value of sigma, which is the density, and then you calculate the mass. Now, you plug in this value to get the Ixx of the semicircle, but we are not finished yet, because we want to know the Ixx of the composite object, that is the moment of inertia about x axis from the composite object, which is the moment of inertia of the rectangle minus the moment of inertia of the semicircle. So, we have derived the value of moment of inertia of the rectangle and the moment of inertia of the semicircle here. So, take the difference and show that okay. So, there is a unit, it should be show that you check the numerics, then you indeed get this, whether you get this particular value. So, here I mentioned that the sigma, which is the density, which is 1 gram per millimeter square. Now, I show you some example of a typical kind of engineering machine where you apply this concept of moment of inertia, is something where you have different kinds of shapes like W or S or C or angles, which are used as parts of different machine. And you need to know, if you have different machines which are rotating with respect to each other, then you need to know the moment of inertia. And so this will be relevant for those of you who will be taking mechanical or civil engineering from those disciplines. So, you may encounter this kind of list which of different sections. So, these are called sections, and they have different geometrical properties. So, it may be listed as shown here, and this is the column which calculates the moment of inertia. So, there are several other properties which we are not going to discuss now. So, note that this is given in the unit of millimeter 4 So, this assuming that it's independent of the density. So, we are assuming here that the density is independent and basically density is 1, the density is 1 unit. So, this is where in a real life situation, and then the point is note that these shapes, these are neither our simple shapes. So, these are more like an composite object. So, this is the practical situation which is kind of where in a real context where you need to calculate, at least those of you who are engineering students will require to calculate moment of inertia. So, to summarize what we discussed today is basically we took the most general definition of moment of inertia. So, now we are kind of learned moment of inertia not only in 2D, but also we generalized to 3D, and we take an example of where we applied the various standard result as well as parallel axis theorem etc. to calculate the moment of inertia of a composite object, and we showed a real life situation of composite objects where these kind of calculations are necessary. In the next lecture, we are going to introduce a new concept which is called product of inertia. Thank you.